So yeah, now we're talking about conformation. This is showing you with hydrogen peroxide, H2O2, and how you can have different angles between relatively with respect between the two hydrogens. And the important thing about this is it's called a dihedral angle. Okay? So this is a term that you probably have not heard of yet. Where did I put? I just had it. It's a dihedral angle. In geometry, how many points does it take to make up an angle? 3. Because why can you not have an angle between 2 points? What is it if you only have 2 points? It's a line. All right, so, point A, B to C, we're talking about this kind of angle. That's an angle that you've learned of in geometry. All right, so angle. Dihedral angle is the apparent angle that's made by 4 points. Just blew your mind, I'm sure. All right, because we're talking now in the 3 dimensions, and so you can actually have an apparent angle with 4 points. I'm going to demonstrate that, or this. So we're looking at now carbon, carbon, hydrogen. Remember, this is in 3 dimensions. So it actually really matters where our eye is looking at. Since I've got blue eyes, I'm going to use blue for here. Whoop. And so I'm looking straight down the bond between the 2 carbons. So this is the bond I'm looking at. And so I'm going to be moving the little hydrogens, sort of like propellers or flagella. So it's not faith integration, but it's biology integration. That should be worth something. But you can imagine that they're moving around. And so that's why I pass these around. See, they can move. Yay, yay, yay. And so there are different conformations. The 2 extremes that you have is if you look straight down like this, like you're looking down the barrel of a gun. Legal disclaimer here. Please do not look down the barrel of a gun. But we can see that the hydrogens are perfectly lined up. Whereas if we go just 60 degrees, they're perfectly not lined up. Okay, so there's this, when they're perfectly lined up, it's called eclipsed, because so just like a lunar or solar eclipse when the planets align. That's why this is called eclipsed. When it's 60 degrees apart from each other, it's called staggered, because they're staggered from that dihedral angle. All right, and so let me see if I can. There are different ways to draw this. One of the simplest ways, I forgot the official term, but I like to call it the sawhorse method, because you can imagine this being a carbon. I'm sorry, let me do a different color. So we have carbon, the front carbon, we have the back carbon. And so we can imagine hydrogen, 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 hydrogen. And so whenever they're perfectly lined up like that, that's when it's called eclipsed. Or you can imagine it carbon and carbon. I'm sorry, that's not eclipsed, it's staggered. No, it's eclipsed. This is when staggered. That's what happens when my mind goes faster than my mouth. Or vice versa. Okay. To where if you look at this specific dihedral angle, whereas your eye is looking down this, it's going to look like it's 60 degrees. There's an even easier or better way to draw that, and it's called a Fisher projection. Wait a second. I'm sorry, it's called a Newman projection. Fisher projection is something else. All right, so the way that you draw, and I'm going to use 2 different colors. So here, whoops. Here we have the front carbon with 3 things hanging off. And then in this color, we've got the back carbon that I'm going to draw as a circle with its 3 hydrogens hanging off. And so this one's called the Newman projection. Let me make sure I spell it right. Yep. Okay, so the apparent angle here is 60 degrees. I mean, if you don't believe me, you can go up and figure it out. Takes a little bit more time to figure out 60, 60, 60 times that by 6 is 360. Okay, whereas you can draw the Newman projection and draw it. Here, let me. Voila. So we have the back carbon you've got the front carbon. And a lot of times when they draw this, they draw it slightly off, so it's not exactly 0 degrees, just so that way you can tell one from the other. Okay, of course I'm using different colors. Whenever you're drawing, it's fine if you just draw it, especially if you say, okay, this one is eclipsed. So the apparent angle there is going to be 0 degrees. Okay. One of these is actually higher in energy than the other. Which one do you suppose is going to be higher in energy? Means it's a little bit more unsteady, a little bit more less stable, I should say, than the other. They're both relatively stable when we talk with respect to ethane. But is it going to be eclipsed, where the hydrogens are lined up? It's going to be less stable and higher in energy, or is it going to be the staggered that's going to be less stable and higher in energy? It's the eclipsed, okay? Because remember, there are hydrogens here, and hydrogen is small, but it does take up some space. So you could imagine that whenever they're perfectly eclipsed, there's a little bit of bumping and grinding going on right there. That's not necessarily a good thing. So that's called steric strain or steric hindrance. Sometimes people also say steric interaction, but just steric means that their electron density is going to start to rub against each other. And you're going to imagine if you get big enough, like the skateboard and the cane, that's completely sterically hindered at that point in time, because you cannot have them occupy the same space. Okay, and so they would start to hit each other. So like steric interaction, steric hindrance. Some people like to use the word torsional strain. I think it probably goes through all the different definitions, but it all means pretty much the same. Okay. So this just shows you ethane. This shows you some of the different ways. Oh, it is a sawhorse. I didn't completely make it up. All right, so here we see the two different ways of looking at it. They use different colors. You can see the Newman projections, the sawhorses, and so on and so forth for eclipse versus staggered. Okay. And once again, this is called a torsion or a dihedral angle, which is just that angle that's formed. I don't like the way that they call it, with between two bonds and blah, blah, blah. It's between 4 points, okay? 4 points. I mean, their way is also correct, but it's just easier for me to think of it in that way I always explain with biochemistries with your hands and your shoulders and that shadow that it makes apparently. All right. And I'll explain what those funkier terms are in just a moment. So here, this shows you, do not memorize these numbers. Whoops. Forgot they're not talking to each other. Do not memorize these numbers. You probably say, what numbers are the other one? Okay? But it just shows you, whenever they're eclipsed, that it's just slightly higher in energy. It's roughly around 3 kilocalories per mole. And whenever they are staggered with respect to each other, the hydrogens, then it's a little bit lower. But it should make sense. You hold it still. You know, it's eclipsed, it's a little higher in energy, you rotate it by, and you only rotate one. We rotate 1 by 60 degrees. And now it's a little bit lower in energy. You rotate 1 by 60 degrees again. Then it's going to be the same as it was before, so on and so forth, okay? So now let's move up. You can do things with propane versus butane. Propane versus ethane versus butane. And I'll just do one quick example with propane. Maybe. Whoops, sorry. That's supposed to be a straight line. Of course, this is from 0, 360, 180. So in this color, I'm only going to do 180 degrees because as you saw, it just cycles over and over and over again. But whenever it was eclipsed, it was higher in energy. You come down here, it was lower in energy. 120. So this is supposed to be a straight line, but I'm horrible at making straight lines. So that's why if you ever draw one of these for me, it's fine if you go ahead and do it this way. That way I can see 120 is going to be back up where you started, like so. Then 180 is going to be back where the lowest point that you had before. Not drawn to scale, but you get the idea. So that's one of them. Here's the other one. Or actually, I'll just say that one was, let's say, was the ethane that we looked at before. Now with propane, I'm just going to draw one of the examples of propane. We have our front carbon. We have our back carbon. Propane looks like this. And we've got our eyeball looking down that angle right there. So that front carbon, that very first one I have, what are the three things hanging off of it? What are the three things hanging off of that front carbon? Hydrogens. So put hydrogens in. Now I'm going to be looking at this back carbon. That's the circle. I'm going to draw it as the eclipsed form. Okay. And I'll switch colors so it's easier to tell one H from the others. So off of this carbon right here, what are the three things hanging off of it? What's one thing hanging off of it? A carbon. And it's a carbon that's got three hydrogens. See, I can cheat because I can use two different colors, but you'd have to be a little bit more neat whenever you're writing this in your notes. What's another thing that's hanging off of that carbon right here? Hydrogen. And the third thing? Hydrogen, because the fourth thing is the front carbon, which is that little dot. Okay, so it's eclipsed. Now, just comparing that to the ethane that we talked about before, do you suppose that when it's eclipsed, is it going to be the same in energy, higher in energy, or lower in energy? Whenever it's eclipsed. So now we've worked our way up. Okay, so whenever this is eclipsed, is this going to be the same energy as ethane, higher in energy than ethane, or lower in energy than ethane? Higher, because you've now, instead of just having two hydrogens, you've got an entire methyl group that's bumping and grinding against that front hydrogen. And so that's why I don't expect you to know the numbers, but it's going to start up something like here. Okay, it's going to go down. It probably, honestly, wouldn't go down as low as the other one, because even though it's at 60 degrees, this takes up more space than the hydrogen would. Once again, I would not expect you to memorize these numbers, except to be able to talk about their relative. That should be the same height. See, that's what happens when I... That's really not straight line, but you get the idea. Hopefully it's supposed to be a straight line. Just like this one's supposed to be a straight line. And it goes back down, like so. Okay. Now let's start talking about butane. Butane has 4 carbons. Hopefully you know that. Consuela's letting me know that there's lightning in my area. In case you don't know, Consuela is my phone, which I accidentally said something that she heard that she thought was her name because she last hour started talking to us in class. All right, okay. So now we have butane. Now this one, it really matters which angle we're talking about. So I'm going to draw butane a little funky looking right now. CH3, carbon, carbon, CH3. So how many hydrogens are hanging off of that second carbon? 2. I mean, it doesn't really matter. And same thing with this third carbon. Okay. But I wanted to draw it this way because that way you can see there's my eyeball, and I'm looking at the angle between carbons 2 and 3. Okay, so now this is carbon 2, this is carbon 3. Now we're talking about this dihedral angle. being formed. Right? So 1, if we start, it doesn't really matter if you're drawing this on your own, which I have been known to ask this on quizzes or pop quizzes and on exams and things like that. If you draw this on your own, it doesn't matter where you start as long as you define it. So I'm defining this as 0 degrees, where both methyl groups are they staggered or are they eclipsed with respect to each other? They're eclipsed. So both of them are eclipsed. Okay. I'll move that over there. Okay, so that was my 0 degrees. I move it 60, which I have to look at this one. If I move it 60 degrees, I guess it doesn't really matter whichever way, but we move to 60 degrees. You suppose it's going to go up in energy, or it's going to go down in energy? It's going to go down. Okay, and so there we go down. Okay, so the Newman projection here at 0 degrees looks like this. And if you don't mind, I'm going to draw ch3. I'm going to define it. And it's fine for me on like on a quiz, like if we did like a pop quiz or an assignment in here or on your exam for the handwritten parts. Rather than writing out ch3 every time, if you just wanted to write me for methyl, okay, because it's a little easier and quicker. Or instead of writing out propyl, PR, or something where you define it, you can call it R if you wanted to. You just define what it is. Okay, so for the back carbon, or the front carbon, I'm going to put it in black. That was a methyl group. Hydrogen, hydrogen. And then we have a methyl group, hydrogen, and hydrogen. So here at 60 degrees, we said it was lower. It's going to look like this. And I'm only going to move the one that's in the lighter color. Okay. So if I move it another 60 degrees, oh, I forgot to say, is this staggered or eclipsed? Staggered. Okay, and so you can write that on there if you wanted to, like eclipse, staggered, eclipse, staggered. All right, so then we have this one. Is this one staggered or eclipsed? This right here? It's eclipsed. We have a methyl group that's perfectly aligned, just like you can have a lunar eclipse and a solar eclipse or whatever types of eclipses that can happen. You can have one here. This is eclipse, this methyl group and the hydrogen are eclipsed, okay? With respect to each other, and this methyl group and the hydrogen eclipse with respect to each other. So do you suppose, based off of 60 degrees, is that going to go higher in energy or lower in energy than the last one? So I'm trying to say is 120, this one, is it going to be higher in energy, lower in energy, or the same in energy? It's higher. Now, is it going, compared to 0 degrees, is it going to be higher, lower, or the same? A little bit lower. Okay? It's not going to, and the reason why is when we were here, we had 2 big methyl groups bumping and grinding. Not good. Here, we just have a methyl with a hydrogen, a methyl with a hydrogen. So yes, they're not perfectly happy, but it's not as bad as having 2 methyl groups. And so I'm going to start drawing some lines in so that way hopefully I can get so it's somewhere right around here maybe. On your own, I suggest that you write in the, well here, I'll write it in for this one. I won't write all of the Newman projections for every single one because I just don't have enough room on my iPad to do that. But I will for this one. Okay, so this is 120. Hopefully you don't mind if I take a little bit of time to do this. Methyl, hydrogen, hydrogen. But now they are Methyl, hydrogen, and hydrogen. Okay, now we go from the 120 to 180. Okay, so is it staggered or eclipsed? This is staggered. Remember, we're looking at this bond here between carbons 2 and 3. I'll give you a moment to draw the Newman projection. All right, so just quickly, we have for 180 degrees. Now, and I had you guys do your own Newman projections for it, but with the 180 compared to 120, is it going to be higher in energy or lower than energy? Is this higher or lower in energy than 120? Lower. It's lower. Now, when we compare it to 60 degrees, is it going to be higher, lower, or the same? Lower. It's even lower. Okay? Because the metal, the two biggest groups, are as far away from each other as possible. So it's the lowest in energy. Okay. All right. When it's this point, when we are saying that they are as far away or they are the opposite of each other, it's given a special term. This confirmation is given a special term. It's a prefix that means opposite, okay, or against. So like Christ and Antichrist. I know it's a stretch for configuration there, but this is because I can get gravity and anti-gravity. So it's the anti. This is called the anti-confirmation. So, which I didn't have it drawn out, but that's called the anti. When they were perfectly lined up, when you have the two methyls where they could bump and grind each other, that's bad. So this is one time when anti was good, I guess. Bad. This confirmation when they are really, then the two large groups are perfectly eclipsed with respect to each other, is called sin. Okay? It's not spelled the same way as sin, but you can think that sin is bad. So it's sin as in S-Y-N. So we have those are the two extremes. So now if we go to this was 0. This is 180. If we go to 240, are we now eclipsed or staggered? It's eclipsed. So it's going to go higher in energy than anti or lower in energy? Higher. Is it going to look like be the same as any of the others that we've seen before? Pardon? It's going to be the same as 120. To where, once again, if you just draw all your Newman projections, what you would find out is it would be identical. It's just that methyl group, I forgot this one lets me do it. This methyl group that we had right here is now up against that hydrogen right there. And so otherwise they're identical. So it's what, 240? Whoops. Not very smooth, but hopefully you get the idea. Okay, so we go to 300. When we look like this, is it staggered or eclipsed? Pardon? It's staggered. Okay, is it going to be higher than the last structure in energy or lower? Lower. Is it going to be the same as any of the others that we've seen thus far? 60. It's the same as 60. Once again, if you do your Newman projections, you would see that that's true. This doesn't. And then if we go to 360 degrees, is it going to go up in energy or down in energy? Up, because it's going to be the exact same thing as what we started off with. Like that. Okay, so we had sin, the special names. So sin is bad. We had anti, and at least here anti is good. Then we had, if you notice, we got that one time when even though they are staggered, they're not as low as they could be. Okay? So we have those two localized minima, if you think back to calculus. Those are given special names. That's called gauche. Gauche is when the two large groups are staggered with respect to each other. So yes, it's lower in energy, but not as low as what you would expect. Not here as anti, or not the lowest it could be, I should say. Once you get used to this, you would expect it for something to be gauche. Okay. All right. So sin bad, anti is the lowest in energy. Gauche is whenever the two large groups are apparently 60 degrees apart. So it's higher than what it would be compared to the anti. All right, so this is what this is just showing you with words. All right, gauche. But if you're taking time to draw it out, use the models. Make sure you get back the models, because this is the only one I have. Into the class. And then if you wanted to see a prettier picture, they're beautiful. Once again, do not memorize the numbers. I do want to point out the difference between the sin and the anti here is larger than it is for propane, and which is larger than it would be for ethane, whenever they are, eclipsed, which makes sense. We're talking about two big methyl groups versus, two hydrogens in ethane versus a methyl group and a hydrogen in propane. And you can imagine, what would happen if we went up another, carbon to where we talk about pentane. On your own, I would expect you to be able to try to figure out the relative energy diagrams, be able to draw it, for pentane, hexane, for any structure that I gave you at this point in time. So you can imagine here, if we're looking down the barrel of the gun, once again, please don't look down the barrel of the gun, but you can imagine at some point in time, whenever they are sin with respect to each other, they can actually invade each other's space. In fact, what we find out is they can actually, when we get to 5, it can form cyclic. Okay, but you can imagine if it's linear, that would be bad. That'd be the highest in energy whenever they would be, because they literally are bumping and grinding into each other. So it'd be like the skateboard and the cane hitting each other.
Will you orient it and tell us which carbon we're looking at?
Yeah. I would say between carbons 2 and 3, carbons 3 and 4, carbons 1 and 2. Mm-hmm. But I don't care so much. Unless I gave you a specific angle to start off with, I wouldn't care as long as you said, this is my 0 and this is my 60, 120. Make sure that it does follow 0, 60, 120. I had one student who would do 0, 180, 240, 60. I'm like, I can't grade this. It'd take me an hour and a half to try to figure out what's going on here. Okay. All right. So we can see here, maybe. Once again, I've already talked about this, how staggered are the localized minima versus eclipsed will be maxima, if you think back to calculus. If it's a larger group, like a methyl group, then obviously versus a hydrogen, whenever they're eclipsed, it's going to be larger than what you'd expect a hydrogen would be. All right. Oops, sorry. Unfortunately, whenever it tried to, it didn't resize the picture. So I'll just tell you what that says there. So why do we draw, actually, This is the reason why, like with pentane here, the reason why we draw it kind of zigzaggy looking like that is that way you can be all anti. Let's see, anti. Let's see. Anti. There we go. Okay, so that's why it makes it, when you zigzag it, zigzag, you get the idea. Then it makes it all anti with respect to the carbon right before it. So that's what they're saying here. That's one of the reasons why they like to draw it this way. It gives it a little bit more functionality. That's the lowest energy structure for it. Okay, so I've already mentioned this next point with respect to pentane. So what happens when they form cyclical groups, become cycloalkanes? This is just true geometry. I usually would ask students. Usually students could figure out the angle of a triangle is 60. They could figure out that 90 was a square. But then they would forget geometry from then on. Okay? All right, so if you go to 5, to a pentagon, it's 108 degrees. 6 is 120, 7 would be 129, and if you went to 8, would it be higher or lower than 129? The angle between the carbons. It's even higher. I can't remember what it is. And the reason why, because, in order to have 8, it's got to go a little wider out, and so on and so forth, to make that circle. Okay? And so if this is true, as it kind of argues it away, you would expect cyclopentane to be the most stable. Okay? Because it's the closest to that perfect tetrahedral angle. Remember, once again, that's 109.5 degrees. Okay, so since the ideal is 109.5, you would say, okay, cyclopentane has got to be the most stable. Then the next most stable one would be cyclohexane. Then it would be cyclobutane, and so on and so forth, right? 109, that's 29.5. No, take it back. It would be cycloheptane, then cyclobutane, and so on and so forth. Okay? However, if you look at the heats of combustion, remember that's a way that you could dictate or kind of figure out. It's not true. Cyclopentane is not the most stable. In fact, it's cyclohexane. So if we look here, cyclohexane, we get 156. Whereas if you go to pentane or heptane, they're just slightly higher in energy. And so why? The problem that they had before, and it's called von Brea ring string theory. I don't care that you remember the name of the theory so much as you just get the idea. What was the one exception that they were making when they were talking about that? Whenever they had 3, it was a triangle. Triangles are 60 degrees. Squares would be 90. Okay, which if I try to do this, like you would have to, the reason why it's so unstable is, look, I'm having to bend, in fact, I'm not even going to do it because it'd break the model. You'd have to bend the plastic, and so it's not happy. Whereas if you've got 5 actually forms pretty good cyclic group. It's not the most stable, but it's the second most stable. So what's the one exception? What were they assuming before that is not true? If you think about this and look at it in all sides. It's not planar. See, it's kinked. It's kind of kinky. Okay? If you do 6, it's even more obvious. So the von Brea or whatever his name was, he was, years ago when he was a theoretical chemist, before they could determine the structure of these in 3 dimensions experimentally, that's what they just assumed it was like geometry. But I shouldn't say that he'd feel stupid now, but the fact that it was like the person that made all the credit afterwards and proved him wrong. Like he's like, oh, that's so easy. He forgot the fact that there's a third dimension. He's looking at things on a piece of paper. Give yourself a moment to figure that one out. But yeah, if you draw something on a piece of paper versus if you assemble it, no, a square versus a sphere, so to speak. All right. So now if we have 6, in fact, what we're going to find out, 6 in what's called the chair conformation, it's the exact 109.5. That's the reason why. So this is not the chair. This is the book. Always have to do it this way. This is the chair. 3 up, 3 down. It's called the chair because it kind of looks like a little chaise lounge, but it's actually 109.5 degrees because it's not planar. It's not like a quarter, okay, which is all, you know, a circle, but it's a nice 3-dimensional structure. I was going to attempt to draw that, but I think I'll wait and show that one later. And I'll let them draw it. Here, we don't want to see this. See, that just shows you cyclobutane. It can't be a square. You can see it's puckered in 3 dimensions. It's still not happy. But you can get cyclobutane, but this is not happy. Okay. Whereas I don't have a picture there for one of cyclopentane in 3 dimensions, but I showed it to you with the model.